Okay, with the comparison of the natural growth in logistic models, in the 1930s, the biologist G.F. Gauss conducted an experiment with the protozoan Paramecium and used a logistic equation to model his data. The table gives his daily count of the population of protozoa. He estimated the initial relative growth to be 0.7944 and the carrying capacity to be 64. So here's the value of t, which is going from 0 to 16. And then the Paramecium, the observed, you can see what the values are as far as the outputs. Now for example 4, we want to find the exponential and logistic models for Gauss's data, and then compare the predicted values with the observed values and comment on the fit. So for part 1, if we want to find out what is the exponential model, so if we're looking for the exponential model, well, we know that the value of k is 0.7944, and we know that the initial is 2, since we can see that from our table here. And so P of t is going to equal the initial population e to the kt, and so we have that information, so there is the exponential model. Now, for number 2, we want to be able to determine, okay, what is the logistic model? Well, before we do that, we know the carrying capacity is m, which is equal to 64. And we have 1 over the initial population times the derivative of p with respect to t, where t is equal to 0. So we have k, which is the constant, times 1 minus the initial population 2 divided by the carrying capacity, which is 64. And that's approximately k. So in order for us to find the logistic model, we know that from our equation in our previous exercise that P of t is equal to m over 1 plus a times e to negative kt. And we know that the value of a is equal to the carrying capacity minus the initial population divided by the initial population. So if we take a look at that, we know that we have the carrying capacity, 64, divided by 1 plus a times e to negative 0.7944 t, and that was the value of k. And then in order to find out what a is, we would take 64, subtract 2, and divide it by 2, and so we would get 31. So now we know that our logistic model, P of t, is going to equal 64 divided by 1 plus 31 e to negative 0.7944 t. Now we would then use these equations to calculate the predicted values rounded to the nearest integer. So at the beginning, these particular problems were already worked out. So if we look at the logistic model, we can plug in the value of 0 all the way up to 16, and we're going to get those values in that row. Okay, and then if we look at the exponential model, then the exponential model, plugging in the values of t, meaning the days, then we would get those results. Okay, so what do we notice from the table and from the graph in figure 5? That for the first 3 or 4 days, the exponential model gives results comparable to those of the more sophisticated logistic model. So we have the observed 2, logistic is 2, exponential is 2. The observed is 3, we have 4, and then 4 here. After 2 days, the observed is 22, 9, and 10. And then 17, 22, 28, and 48. And then at day 5, you can see what's happening here. So for t being greater than or equal to 5, the exponential model is hopelessly inaccurate, but the logistic model fits the observations reasonably well. So here you can look at figure 5, looking at the exponential and logistic models for the paramecium data. So here we can see that the exponential model increases. Here we can see that the logistic model starts leveling off at a particular amount. In this case here, you can see it was 64, which is the carrying capacity.